As usual, I will put the link of our recording in our Degler class. When we started Degler 2, old Degler pa tayo, no? Nowadays, we are now in the modern Degler. Okay, so it will be the same, no change. So anyway, if you have logged into your, I have a syllabus there. I have just uploaded it this morning. It is almost the same sequence here. Now, previously, this is a 5-unit course, no? Salvador, okay? This used to be a 5-unit course, which has been reduced to 3 units because the laboratory was removed. It's a good thing that it was removed before the pandemic so that we don't have to do any laboratory work, okay? But some of the laboratory work we'll do on using a using a software, no? Salvador. Okay. You will still do certain experiments. Now, if you look at, we have an experiment manual, but we will only do it in, we have a lab manual, but we will do it only on CEDAR logic, simulated lang, not actual bread. We will not use actual circuits. Although you can look at these videos, for using the circuit breadboard, the digital integrated circuit. Our book is eRoth. I think there's a modern version, but anyway, I have changed this a lot such that many of the sources are from the internet and other sources and other books. Wala. Anyway, you can download that, itself. Pwede mo namang i-download ito. It's a PDF. Okay. So, to describe this is an introductory course on hardware. Do you follow? Did you have a physics course before this, electronics course? Everyone?
Yes po, sir. Basic electronics, sir.
So, you took up transistor biasing? Yung paano mag-bias ng mga PNP and NPN transistors, base bias, collector bias, and emitter bias? Meron ba?
Nadaanan lang po namin, sir, but we did not go in depth, sir. I think.
Kasi gagamitin, we will use that in this course, transistor biasing, although it's just in passing, but when we discuss flip-flops, later. And then you're familiar with circuits. You have used circuit boards, right?
Yes, sir.
So you know how to connect. We have a video here, and we will review the pin layouts of the integrated circuits. We will not be doing them physically anymore, So hanggang simulation lang tayo. But you must have an idea on how actual logic circuits are constructed physically, physically constructed. We used to have that when in the old curriculum, when this was a 5-unit course. But now this is a 3-unit course, so we have to make do with what is given. Okay. So introductory to hardware, and this also serves as a prerequisite to your next course, which is computer architecture. So this is in the hardware track. Okay, do you follow? So anyway, so if you look at the if you have time, towards the end, kasi dati when this was a 5-unit course, we will have an introduction to computer architecture. Using a different textbook. We will use architectures that were predecessors of the Intel 8088, yung sa IBM PC. Ito, SAP1, SAP2, these are simple as possible architecture. SAP3 is like Intel 8088, which is the predecessor of the Intel processors that we have now. Okay. This is the origin, by the way, of the Intel processors that we have now. Ancestors, not predecessors, I'm sorry. Okay, any questions so far? So if you look at the topics, we'll start with number systems. Why is that? Because computers always process using binary numbers. Do you follow? And then we look at Boolean algebra. We start with logic gates, okay, and how to manipulate Boolean expressions, because digital design process starts with construction of Boolean expressions and conversion into actual circuits. Like for example, mathematical calculators, no, scoreboards. Okay, they are Boolean algebra expressions, which are used to, which are then converted into actual circuits. We look at digital integrated circuits, no? How ICs, no? Have you seen an IC before? Let's look at other images. No? Baligtad dito eh. If you have an IC like this, no? This is an IC. Bakit ibang lumabas? Ito. Okay. Usually there's a notch here, and there's a circle. There's a circle notch also on the other end. Okay. This indicates the lower end and the opposite end as the upper end. Do you follow? And the numbering of pins starts with the left side of the lower end, going upwards, no? And then to the other, going to the other side, and then going downwards. No? Pin. So ito yun, no? So there's a notch here, no? It starts with the right side pala. So this is pin number 1, pin number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's how you put it there. Okay? So usually, the power supply is connected, I think, on the left, the right hand side, no? Saan ba ang power supply? Hindi naka-indicate. Ito, no? If there's the power supply and the ground is on the opposite, the diagonal opposite pin. So, dito ka this is where you connect the 5 volts source, and this is the negative ground, okay? Diba? If you've done electronics, right? So you know where the power supply we use is usually 5 volts. No? Okay, so ganito. So this is the VCC, this is the ground. Okay. So if you look at the inside, there's a demonstration. This is CMOS NAND gate. So this is a quad 2-input NAND gate, which means there are 4 NAND gates inside. Okay. So we look at integrated circuits, and then we'll have a formative assessment. Then we'll discuss constructing. How do we construct logic circuits? We using simplification theorems, no, mathematically, and then we will use the consensus theorem, and then okay, basic logic circuits in Cedar Logic. We'll construct the logic circuits using a software, no, called Cedar. Have you used this before? During the time of Father Denny, they use Logisim. Okay, Logisim. Do I have a Cedar Logic? I think nandito pa, no? I'm sorry. Cedar Logisim ang ginagamit nila. This is where we construct circuits as a substitute for a breadboard. This is like your circuit breadboard, no? Where you can make connections of different gates. And then, okay, you can connect them together. Okay, let's change this. This is Cedar Logic na. Okay. Ganyan. Okay. Then we can connect this to an output. Okay. And then we can connect input. On off toggle switch. This A. Okay. Ganun lang, di ba? Anyway, let me finish this and show you what happens. No? Okay. Like this. This is Cedar Logic. You should start downloading this already. No? And then we can have text. So we have text. Text. Okay. A, input A. B. Pwede namang ano eh. We'll just remove this. Para mas konti lang. And then we'll use an inverter. This is an inverter. Can we connect this to ano? Hindi na natin ma-connect, no? But we will have connectors like this. Okay. So that we can transfer this here. Okay, and then we can connect this here. Ganun lang naman. Then we have another connector. So we can connect this here. I-delete muna natin ito. Then we connect this here. No, mali. That's the wrong connection. We connect this here. And then we connect this there. Okay. And then ito, habaan natin. No. There. Okay, I'm sorry. We remove this. This is wrong. Ito, i-connect natin dito. Okay. And so on and so forth. Anyway, so pag on off mo, makikita mo kung you can get the result here. No? An on is a red, an off is a black. Let's just put this to a 1. Can we put a 1? Okay. Lagyan natin dyan ng input. Okay. Let's put a 1. Okay. So you can change the input because this is an OR. So let's close this. No. Okay. So a black is a 0. A red is a 1. Okay. That's how you do it. Now you can also connect graphs. No. Okay. You can connect decimal display output. No. So that's what we'll do. We'll discuss this no in detail later. No. And then we'll bakit wala pa tayong ano? We'll take up construction design logic. Saan ba yung design? Arithmetic logic unit here, no? We'll discuss arithmetic logic units. We'll do an experiment. You download the experiment manual, no? By the way, let me show you that later, no? And then you will we will do, no? Boolean simplification. First, we will use, the classic Boolean algebra. And then there's another method called kanina ba yan? K-mapping, no? K-mapping. And then we will introduce soft programs, algorithms that are used to implement K-mapping. Particularly, there's a Petrik's method and Quine-McCloskey. No? These are algorithms used to implement Boolean simplification. No? Actually, there are C# codes or C++ codes which you can download, no, to run or to run Boolean simplification. Okay, which means you can input a complex Boolean algebra expression. It will give you a simplified version. Okay, so maganda, no? Okay. Petrik's method we will discuss. Una, we will use non-time dependent circuits, no? Dito, we will use flip-flops which are synchronous circuits which are time dependent. Okay, and then from flip-flops we will study registers and memories. Okay, because registers, counters, and memories. Flip-flops are the basic foundation of Boolean memory. Okay. So pag registers, we'll study the different types of registers. The ALU, the CPU registers, yung counters, no? Buffer registers, memory address registers, data registers, and so on and so forth. Counters, no? By the way, no? And then if you have time, we'll take up no, essay, computer architecture. Remember, this is an introduction or prerequisite to computer architecture. Any questions? No? 70-30 tayo dito, no? Which means your experiments, your assignments will take 30% and your formative assessments will take 70% of your grade. Okay? Any questions so far? Okay. No questions? So, you've gone through intro to computing, right? One of the topics that were introduced there is numeric representation. The very first thing to study when you're when you are dealing with computer design is the representation of numbers. Okay, you can download this now, and we will discuss binary subtraction and converting to positive numbers. Converting positive numbers to negative. Okay, let me close this. You can download by the way, Cedar Logic from here. There's a site. There's a link here where you can download. No? I think where is that? Anyway, if it's not there, I'll put it there, no? Or you can just Google Cedar Logic and it will bring you to the download site. Okay. Cedar Logic. Meron pala sa SourceForge. Okay. You can download Cedar Logic from there. It's free. 70-30 yung assignments and experiments. And then 70 yung formative assessments. That's because bakit 60-40 ba sa iba? Dory?
Yes, sir. Yes, sir. 40% sir kay PAA, sir. Anya, pag 60% kay summative, sir.
Ganun ba? Sige, I'll try to adjust, okay? Kasi that's the usual, I-adjust ko pala yung iba. Dati ba tayo sa sa databases, ganun ba? 60-40? So anyway, I'll try to adjust, okay? Because you will have a lot of exercises anyway, no? You will have about 12 experiments. And then problems to solve, no? You will have a lot. Okay? You remind me, no? Because I'll update anyway, I'll update it as soon as we're done, okay? Okay? So, numeric representation tayo. Downloads. Okay. So, any questions so far? The number systems, no? What is a number system? A number system is a method of recording that is used to represent quantities, right? And we are very familiar with the decimal system. Okay, symbols and their equivalent quantities. So we count by 1 to 10, right? 11, 12, 13. So it's the decimal system. In a decimal system, numbers are grouped into powers of 10. Like the first number or the first quantity being 1 to the 0, or rather 10 to the 0. No? 10 to the 0 is anything is raised to the 0 is 1, tama ba? Yes. 10 to the 0 is 1. The next number is 10 to the 1, which is 10. The next number is 10 squared. which is 100. The next number is 10 cube, which is 1000. No, so it's an ascending series of the base. So a decimal system is a system whose base is 10. Do you follow? So 10 to the 0, 10 to the first, 10 to the second, 10 to the third. As we go on, no? So there's in any number system, there are always symbols, right? 0 to 9. These are the basic symbols. No? They represent units and represent very small quantities. No? Now, when a larger quantity needs to be represented, usually we use a combination of symbols, okay, with different place values. Do you follow? A place value is a multiplier assigned to a location. Okay? Yeah, place value ang tawag dyan, but it's really a multiplier assigned to a particular location of a symbol to represent larger quantities. Diba? Like for example, in the decimal system, 16 has the following place values. The symbol 6 has a place value of 1 or 10 to the 0, diba? And the symbol 1, I'm sorry for the mistake there. The symbol 1 has a place value of tens or 10 to the first power, diba? If you have another, it will be 10 squared. So the actual quantity being represented is 1 times 10, because there's 1 there, to the first power, which is equal to 10, plus 6 times 10 to the 0 power, which is 6. So the equivalent is 10 plus 6 is 1/6 base 10, or we call it 16. You follow? So ganun yung ano, that's always how we represent numbers. To represent actual quantities, we use more symbols with a larger place value. Okay? There are different number systems that are being used nowadays. Of course, people use the decimal system, right? The symbols are 0 to 9, and the base of the place value is 10. Okay? But computers don't use decimal systems, right? Because they're difficult to implement in hardware. No? In fact, if you review your history of computing, no? in ENIAC is the last computer, 1950s siguro, ano? Between 1940s to 1950s, right after the Second World War, 1947, I believe, no? Was the last computer system which uses decimal number system. And the corresponding circuit is a very complex circuit because there's no physical electronic device which can represent all the numbers. Unlike for binary, no, you can use a transistor to signify the value 0 or 1, or a switch. Okay, we'll show you that, no, in our succeeding. Ano. So the binary number system is a system which has symbol 0 to 1, and the base is 2, which means that the place value is, you are familiar with this, right? The binary series. What is the first value place value? Because when you buy memory, no, diba? Memory sizes are in powers of 2, right? Even hard disks are in powers of 2, no? The base is 2, so the first decimal number is 1. The next is 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, or 1 kilobyte. Now, pagkatapos ng 1024, 2048, 4096, 8192, 16. Pag 16, hindi ko na memorize yan. Basta ang 32 something. 32K, 64K. Do you follow? So that's the binary number system. Now, programmers, early programmers especially, cannot use the binary system because they're very long. So a certain number system is used as a shorthand. No? Shorthand to binary, because you can use, no, pwede shortcut yung writing of binary numbers using hexadecimal numbers. You cannot use decimal numbers as shorthand of binary numbers. Only hexadecimal numbers can be used as shorthand. Okay, we'll show you that also later. The symbols are 0 to F. The base is 16. Any questions so far? So when you're doing assembly language, you will be using hexadecimal numbers. Now all programmers in the past also use hexadecimal as a shorthand to binary notation. Okay, any questions so far? So how about characters? How do you represent characters? No? So characters, the letters kasi, no? How do you represent letters? There used to be three popular representations. They are called the coding systems, no? Iko-code natin. For example, there's a binary coded decimal code. Nowadays, no, there's only one coding system used. It's called ASCII, American Standard Code for Information Interchange. IBCDIC was invented by IBM, but was later phased out. IBCDIC was very popular in punch cards. No? Madali siya i-punch. Extended binary coded decimal interchange code. Okay? Questions? Okay? So that the representations. Now, let's go back to numeric quantitative representation, representing quantities. Okay? In binary. So the basic unit, one symbol in binary is called a bit, right? What does a bit mean? Anyone? A bit is a shorthand, right? Okay. A bit is a shorthand for binary digit. When you say bit, it's binary digit. Okay? So a bit can store any of the two quantities. It's either 0 or 1. Okay? Dalawa lang, 0 or 1. Okay? That's the basic unit. The next unit is called a nibble. Do you follow? A nibble is a group of 4 bits. Now, a nibble has an 16.
24 NTLC, 24 pal. NTLC.
So anyway, a nibble having 4 bits can have 16 different values, di ba? 0000, 0001, 0010, 0011. No? So it counts from decimal 0 to 15. You follow? That's a nibble. After the nibble, what's the next group? The most popular group is called a byte. A byte is a group of 2 nibbles or 8 bits. Okay? In any number system, no, whether binary, decimal, hexadecimal, we always distinguish the significance of a bit. Okay? Now, in any number, there's a least significant bit, or in decimal, there's a least significant digit, no? And the most significant bit. Okay? So this has nothing to do with racial discrimination. No? We're talking of numbers. Nobody is lesser significance than any other. In a way, no? Because when you say someone is least significant, he's the most neglected member. No? Anyway, we're talking of numbers. No? We're talking, when we say least significant bit, it has the lowest quantity. The most significant bit has the biggest quantity. The least significant bit is on the rightmost side. The most significant bit is on the leftmost side. Okay? LSB and MSB. Sorry about this. Hindi ko pa ito na-update. So if you have a nibble, no? You have this. This is the first number. This is the least significant bit. And the last number is the most significant bit. The least significant bit has the least place value. Ibig sabihin least quantity. The place value of 1. The most significant bit has the biggest place value, which is 8. Do you follow? So the third bit represents a place value of 2 to the third, which is 8. It is the MSB. No? Tama si Wong. No? Byte. The next bit after that is the second most significant bit. This bit, this is 2 squared, which is 4. And then 2 first, which is 2 to the 1, which is 1. And the last is, 2 to the 1 is 2. And the last is 2 to the 0, which is 1. So for example, if you have the value 1011, this means that there's one group of 8 plus 0 groups of 4 plus 1 group of 2s plus 1 group of 1s, which means you have 8 plus 2 plus 1 is 11 in this decimal. Diba? So in an odometer, the first count is a 0, the next count is a 1. Pagkatapos ng 1, we go to the next most significant bit. So we'll have 1 0. Diba? After 1 0, we'll have 1 1. After 1 1, we'll have 1 0 0. Then we have 1 0 1, 1 1 0, 1 1 1. Okay? That's how we count. No? Any questions so far? No? So a byte is a grouping of 8 bits or a concatenation of 2 nibbles. No? Here are the place values. No? The least significant bit has 1, the next has 2, 4, 8, 16, 32, 64, 1, 2, 8. Okay? So the signed values that are possible are from 0 to 255. So that's why you have 254 characters. 254 ba? Kasi kung including ang 256, kung kasali yung 0, no? 256 pala, I'm sorry, no? For a signed value, ang ibig sabihin ng sign, we spare the most significant bit. We do not use it to store a value, but we use it to indicate a sign. If it's 1, it's negative. If it's 0, it's positive. So therefore, we can only have 128 from positive 127 to negative 128. How do you know the maximum value quickly? Anyone? For example, for an unsigned value, the number is 0 to 255. How do you know the okay, the next value quickly? The highest, kung dito 128 ang last, how do you know the maximum value quickly? Anyone? It's the next place value minus 1. For example, 128, the next value is 256, right? Minus 1, 255 yung maximum value. Kung 64, okay? The next value is 128 minus 1, 127 yung maximum value. For unsigned, kasi 0 to 127 yan, di ba? Get the next, minus 1, okay? Do you follow? So for example, if you have 1 bit, what's the highest value? If you have 1 bit, the next place value is 2 minus 1, 1. Diba? So the highest value for 1 bit is 1. What's the highest value for 2 bits? 3. Why? Because the place value is 4 minus 1, 3. So can we check that one? The first value is 0, 1, then 1, 0, which is 2, and then the next is 1, 1. So 3, diba? If you have 3 bits, what's the maximum value? It's 7. Why? Because it's 8 minus 1. Okay? If you have 4 bits, what's the maximum value? 15, because it's 16 minus 1. Okay? We'll discuss the theory behind that later, no? Okay? That should be binary savvy, no? You should have computer science students should have should be very familiar with the binary series. No? Numeric representation. No? Now, you've done C# programming, right? Or C++. We have to know how these numbers are represented. Do you follow? Okay. In C#, there are integers and there are floats, right? Or C++. Merong integers, merong floats. Okay. Integers are whole numbers. Okay. Now, non-numbers or letters are stored using the ASCII format. Okay. But numbers cannot be stored using the ASCII format. It will take too much space. Inefficient. Remember, you have the number 1, 2, 3, 7, 6, 9 using ASCII. This would consume 6 bytes to store an integer. Do you follow? Okay. While it can be stored by how many? 2 or 3 bytes na using numeric representation. Do you follow? And it would be difficult to tell if the number is positive or negative if we use ASCII. Okay. The more efficient way of storing a number is to use a different coding. Different encoding scheme. No? The scheme is shown as follows. No? Usually, the most significant bit is paired as the sign bit, and then the numeric quantity will be stored in the following succeeding bits. Okay. The sign bit stores a whole number. Okay. Integers do not contain fractions, by the way, no? Hindi pwede. Usually, a sign of 1 is negative, a sign of 0 is positive. No? How do we store decimal or fractional numbers or floats? Okay. For example, these are invalid integers. Diba? This is a valid integer, these are invalid integer because they have fractional values. Okay. Assign integer using 16 bits of the following range of values. So 2 to the 15, 16 bits man siya. 2 to the 15 lang kasi that's the previous di ba? The disadvantage with integers is they can only store a specified number of maximum values. Di ba? Maximum values lang. Okay, how do we represent fractional values like 1/2, 1/3, 1/4, 1/5 in binary? Anyone? Now, likewise, we will have a decimal point. If you're talking about decimal numbers, we will have a decimal point. Now, since we are talking about binary, we will have a binary point. Diba? The binary point separates the integer from the fraction. The left of the binary point is the whole number part or the integer, and the right of the binary point is the fractional part. Okay. For example, if you in decimal, if you have the value 13, it's 1 times 10 plus 3 times 10 to the 0. Right? In binary, the number, this is number 13, no. 110 is 1 times 2 to the 8, I think, no. 8, 12 lang ito. 1, 2, 4. 4 pala, no? 1, 2, 6 lang ito, no? 1 times 2 to the third plus 1 times 2 to the 0 plus 0 times 2 to the 1. May kulang ito, no? Dapat may isa pang 0. May isa pang 1. Okay? Ito. Dito pala, no? The 1 is here. Plus 1 times 2 to the 0. So how much is that? This is 1 times 8 plus 1 times 4. That's 12 plus 0 plus 1. That's 13 also. No? In decimal, we have 1, 3. In binary, we will have 1, 1, 0, 1. Okay? Now, ito ngayon yung fractional values. We'll have the number 0.625. We follow? 0.625. 0.625. Okay? Now, the decimal point or the binary point is an indicator of whether the place values are in ascending series, ascending powers of the base or descending powers of the base. Do you follow? For example, to the right, it's ascending, 2 to the 0, 2 to the 1, 2 to the squared. Okay, do you follow? Going to the right, going to the left, no, it's ascending. Going to the left, it's descending. Okay, so 2 to the, okay, 2, I'm sorry, this is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. So descending tayo. Do you follow? So for example, if you have 0.625, you have 6 times 10 to the negative 1. Do you follow? Plus 2 times 10 to the negative 2. Plus 5 times 10 to the negative 3. Okay? Or in other words, it's 6 times 1 over 10. Because 10 to the negative 1 is 1 over 10. And 2 times 1 over 100. Plus 5 times 1 over 1,000. Do you follow? So descending yung fraction yung ilalim. Now, for example, if you have 0.101, That's equivalent of 0.625. 1 times 2 to the 1 plus 0 times 2 to the negative 2. Sorry, no. 1 times 2 to the negative 1 plus 0 times 2 to the negative 2 plus 1 times 2 to the negative 3. Or in other words, the 1 there is 1 times 1 half, 1 times 1/4 plus 1 times 1/8. Do you follow? So 1, 2, 4, 8, 16, 24, 32 going to the left. Going to the right is 1 half, 1/4, 1/8, 1/16, 1/32, 1/64. Do you follow? Do you get my point? Okay? So madali lang i-memorize, no? It's easy to memorize. Okay. We'll have an exercise with this next meeting. Ngayon, we'll just describe it. No assignment during the first meeting. Okay? Okay? So anyway, I'll check your attendance later, no? Idagdag ko pa. So, how do you represent fractions? The first way to represent a fraction is to use fixed point representation. Fixed point. Can somebody tell me why it's called fixed point? Diba? Bakit fixed point? It's called fixed point because we designate a fixed location of the decimal point. Okay? Do you follow? Like for example, or the binary point. Like for example, when you say 26.5, this is a single digit binary number because we fix the decimal point here. Okay? And when you say 11010.1, there's a single bit binary point. Ito, single digit, 2 digit, okay, 3 digit. Ito, single digit. Ito, single bit. Do you follow? The binary point is the designated divider between the whole number and the fraction Do you follow? To the left is the whole number, to the right is the fraction, okay? (26.5) base 10 is equal to 1101.0.1 base 2. Let's try to find out why. Okay. The first one is 1 times 2 to the 4th, which is 16. Ito 16. The next one is 1 times 2 to the 3, which is 8. This is 8, no? The 0 is 0 times 2 squared. So it's not significant. The one here is 1 times 2 to the 1, which is 2. 2 ito, di ba? And then the next 0 is 0 times 2 to the 0, which is 1. This is a 0, so it's insignificant. Hindi natin sinulat yung 0 dito, no? And the next one, this is 1, is past the binary point. Do you follow? It's now past the binary point. So therefore, we will have a descending series. So this is 1 times 2 to the negative 1 or 1/2. Right? So 1/2 is 0.5. So if there's another one, this should be 1/4. If there's another one, there's a third one, there should be 1/8. But with only one decimal binary point, the last one stands for 1/2, so 0.5. So 16 plus 8 plus 2 is 26. Plus 0.5 is 26.5. Do you follow? Okay, that's fixed representation. Okay. 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 For example, if you are given this number, okay, we know that this is there's a specific quantity. However, if you are told that the binary point is on the third position, right? What's the equivalent? We know that the 1 0 here is 2, di ba? 2 na ito, 1 0, 1 0, di ba? It's like the number 10. 1 0, this is 2. Now the first one is, okay, sandali. Two to the 1, ito yung 2, no? Ito yung 0. 1 times 2 to the 1, that's 2. The 0 is insignificant. The next one is 1 times 2 to the negative 1, which is 1/2. The next one is 1 times 2 to the negative 1, which is 1/4, which is 0.25. The last 0 is insignificant. So we add them together, we know that 10.110 is 2.75. Do you follow? Do you get my point? Now, what is the equivalent of 0.0110? So wala na tayo dito sa sa whole number part. This one, the first one is 1 to the 2 to the negative 1 or 1/2. This 0 is insignificant. This one is 1 to the 2 to the negative 3, which is 1/8, which is 0.125. The next one is 1 to the 2 to the negative 4, which is 1/16. If you do that in the calculator, it's 0.0625. You add them together, it's 0.6875. Do you follow? So in a fixed point number, the whole number part is called the range. Okay. The fractional part is called the accuracy. Okay. The main drawback of a fixed point number is it has limited accuracy. Kasi konti lang no? Do you follow? Any questions so far? Fixed point. We'll do numeric computation, huh? Representation, convert this into fixed point, convert this into floating point. Okay. Balik tayo sa grade 4. We're going back to grade 4 today. Okay? Count numbers. It's not easy, no? Floating point especially. Okay? Especially floating point representation. So there are two problems with integers, no? They cannot represent fractions. The range number is limited to number of bits. Now, also, the disadvantage with a fixed point is it has a limited accuracy. What if you want to represent a very small number or a very large number? That's because the location of the decimal point or the binary point is fixed. Okay, in a floating point representation, the location is not fixed. It can float to the left or float to the right. That's why it's called floating point, depending on which has bigger magnitude, the range or the accuracy. Diba? Kung mas malaki ang accuracy, your binary point will move to the left. If the range is bigger than the accuracy, the accuracy is the fractional part, then the binary point will move to the right. Do you get my point? No? So, an efficient way to store fractions is to move the position of the binary point and splitting it in two parts, an exponent and the mantisa. Diba? Sa fixed point, ang tawag range and accuracy. Sa floating point, what we call them are exponent and mantisa. Okay? The exponent represents the raised value to the power of 2. Yun lang exponent. The mantisa, or sometimes called the significand, represents the fractional value. So, anong mangyari doon sa range? It's now moved away, no? Do you follow? For example, how do we represent 12.5 in floating point? So we have to represent it at 2 to the n times mantisa. Okay? So ganito yung IEEE standard. In a 32-bit number, this is a sign bit, the exponent bit, and the mantisa. A bias of 127, we'll explain that later, no? Anyway, no? Medyo complicated yung yung IEEE standard, no? Okay, we'll explain that later, no? We're running out of time. how do we work out the floating point representation? For example, if we have the number 12.5, we continuously divide it by the value 2 until we get a 0 whole number. Do you follow? Okay. Okay, let's go through that. Okay. First, 12.5 divided by 2 is 6.25. Do we have a 0 here? Anyone? Okay. 6 is not a 0, right? So what we will do is divide it again by 2. So 6.25 divided by 2 is 3.125. Okay. 3 is not a 0, so we continue. 3.125 divided by 2 is 1.5625. 1 is not a 0, so we continue. 1.5625 divided by 2 is 0.78125. Do you follow? We're done when the whole number part is a 0. Okay? We count the number of twos, divisions. 1, 2, 3, 4. 4 is our exponent. Okay? And the remaining number is our mantisa. So in other words, we have a mantisa of 78125, an exponent of 4. Do you follow? So this is 0.78125 times 2 to the 4. Okay? Okay, any questions? We will discuss the IEEE later, no? We will first discuss conversion. Okay, I'd like you to go over the next slide, no? The next slide is there. I'd like you to go over for the remaining, because we're only up to 10 o'clock today, no? Binary subtraction and conversion of numbers. Do you follow? Okay. And we will do, okay, we will need this to construct the arithmetic logic units later, no? Okay. Any questions so far? So one hour lang muna tayo ngayon, no? Next time, by the way, we will have a break in between. Okay. And next time we will have exercises. Okay. So, sino ang hindi naka-ano? Hindi natin nag-count. Sino nandito? Participants. Let's show the participants.
Bergantinos, sir.
Bergantinos.
Mendoza, sir.
Mendoza.
Adriatico po, sir.
Adriatico.
Opo.
Salvador po, sir.
Salvador. And
Lee,
then,
sir.
ha? Lee.
Lee.
Songbin.
Yes, sir.
Yes.
Ignacio po, sir.
Ignas. Linaza. Mabasa pala. Mabasa. Nandyan? Wala. Nebre. Midori, di ba nandito yun sa kanina? Wala.
Sir, ako, sir.
Ha? Midori?
Yes, sir.
Okay. Nandito nga kanina. Nandyan pala. Ochoa.
Yes, sir. Present, sir.
Kibod.
Meron, sir. Present.
So, Razul. Rudolph, wala. So, isang absent lang, no? Okay. Dalawa pa. Oh, how about Mabasa, wala. 2 people are absent. No assignment today, no? We'll start solving exercises next meeting. Okay. For the moment, can you go through the next, binary subtraction and conversion of positive numbers? Okay, I'll give you exercises later. Okay. So thanks for coming, everyone. I'll upload recording for you to review. Okay. Thanks for coming. No, if you have an activity, you can proceed with it anyway.
Thank you, sir.
Thank you, sir.
Salamat.
See you next time, no? Next Saturday. Bye, everyone.
Bye po, sir. Thank you very much po.
Thank you.